we have been discussing about the converging channel or converging nozzle. One important aspect that we have learned out of the discussion of converging nozzle is that if you want to increase the mass flow rate, you can't increase it beyond a point that the Mach number is 1 at the throat, which in this case is the exit of the nozzle. What happens if you want to accelerate the fluid further so that the Mach number is greater than 1? In other words, how do you make an arrangement to obtain a supersonic flow? So, to understand that, we will go for first analyzing the situation through a variable area conduit consideration, that is area variation with Mach number variation. How it happens? If you recall, we derived the following formula. So, this is the relationship between the change in area versus the change in Mach number. We will maybe write it in a corner of the board and keep it somewhere, or maybe if necessary we will write it once more again. So, clearly at the throat of the converging nozzle, if you are interested to get the maximum Mach number, the maximum Mach number that you get is 1. Now, you want to accelerate the fluid further. So, what should be the area relationship with the Mach number? That is what we want to see from this expression. So, if the Mach number is 1 at the throat, we want to further increase the Mach number, that means we want dm by m to be positive. We are at a consideration that we have come to a stage where the Mach number at the most whatever is possible here is 1, and now we want Mach number greater than 1. So, m square minus 1 or m square is greater than 1. So, m square minus 1 is greater than 0. So, in the right hand side you have product of two terms, both of which are positive, that means dA by A must be greater than 0. That means from now onwards the channel should be such that its cross sectional area will be increasing. So, this makes us to arrive at the design of the famous converging diverging nozzle in compressible flow. The question is now as follows: in a converging diverging nozzle, is it guaranteed that you will get Mach number greater than 1 in the diverging section? The answer is no, that is not guaranteed, but there is a possibility that by designing the back pressure cleverly you can obtain supersonic flow at some location in the diverging section. So, how the back pressure will influence the Mach number distribution? We will look into the influence of back pressure with the Mach number distribution in the following manner. So, instead of plotting Pb by P0, we will plot P by P0, which is a variable now because the pressure will vary along the x as a function of x. So, we will consider the following. See, now we will assemble all the wisdom that we have gathered in compressible flows to understand the behavior of the converging diverging nozzle. So, first there is a situation, see, we have to keep in mind that although if the sonic condition exists for a converging section, that must be only at the throat, but it is not necessary that at the throat there is sonic condition, it may also be subsonic condition, it depends on the back pressure. So, this is a situation where we say that it is not the sonic condition, but it is a condition which is having a velocity here at the throat less than that of the sonic velocity. So, let us call this as case A. So, we will draw another graph . M dot by M dot max as a function of Pb by P naught. Pb is the back pressure, which is the pressure at the exit of the nozzle, in this case the exit of the converging section. Okay. Now, so we are keeping the back pressure, keeping the P naught fixed, then we are reducing the back pressure and we are seeing what is happening. So, this is another curve which corresponds to the point B. They are not necessarily parallel, they are looking like parallel. So, I will just maybe something like this. In this way, a critical condition will come when you achieve the sonic condition at the throat, that is here the Mach number, the point where I am putting my finger, at that point the Mach number is 1. So, if that be the case, then at the subsequent downstream there are two possible solutions. So, we call one as C and we call one as D. So, if you recall, we have a formula which I have derived earlier, A by A star as a function of Mach number, right. A star is the hypothetical area at which you achieve the sonic condition. It may physically exist, it may not physically exist, but it is a reference area. So, in this case, if A star exists physically, where is that A star located? The A star is located at the throat, right. So, by substituting A star is equal to A of the throat, and A is the area of the exit in this case, you will get a function of Mach number. This will have two solutions, one a subsonic solution, one is Mach number less than 1, another is Mach number greater than 1, and this origin of the two solutions is that it is, if I remember correctly, it is a quadratic expression. So, it will have two solutions. So, the Mach number less than 1 corresponds to this. Question is this that you wanted, for which you invested the cost of this diverging section? That is not the reason for which you invested the cost for the diverging section, because the whole objective of introducing the diverging section was to accelerate the flow to a Mach number greater than 1 or supersonic condition, that you get here. And therefore, if you keep the back pressure exactly at D, you accelerate the fluid in the diverging section to its maximum potential, and that is why these D, I mean coincidentally it is D, it is called as design condition of the nozzle. So, this is the design condition, this is the design back pressure, that if you keep, you will see that you get the maximum potential of accelerating the flow in the diverging section. In between, what happens? So, let us say there is a back pressure E. So, although the fluid was accelerating to a limit, that, see here the Mach number is equal to 1, and in this case the Mach number is getting reduced, in this case the Mach number is getting increased. So, this line is following reduction of pressure and increase of Mach number, but if you want, if the fluid wants to adjust to the back pressure which is E, deviated from the design condition, then there is one possibility is that there is a normal shock somewhere in the nozzle, and this normal shock adjusts it from a supersonic to a subsonic regime. So, this E is normal shock. So, this symbol is normal shock, you can see that we have drawn it perpendicular to the axial direction. Similarly, you reduce the back pressure more and more, you will see that the normal shock will get closer and closer to the exit of the channel. There is a typical condition, typical back pressure for which there is a normal shock at the exit. And that is the point G. I will try to use a different color now to show you what happens if the back pressure is between G to D, between G and D, say H. So, if the back pressure is located at, is the value located at H, that is between G and D, what we will get is an oblique shock outside the nozzle. So, let us write it here. So, D is the design condition, EF normal shock inside the nozzle, G is normal shock at the exit of the nozzle H is oblique shock outside the nozzle So, oblique shock will have a shock front which is not perpendicular to the direction of flow, and because you are free to control the exit pressure condition or the back pressure condition, you could also have a back pressure which is less than D. You may subject the exit to this pressure, and if you do so, what you get is an oblique expansion wave outside the channel at the exit or outside the nozzle. So, how will the mass flow rates look like? So, the highest back pressure is the back pressure at A. So, if you reduce the back pressure, the mass flow rate will increase. So, you have the point A here, then you have the point B here. So, at the point B you have reduced the back pressure and increased the mass flow rate till you come to a critical condition at which if you increase the mass, if you reduce the back pressure, you will not be able to increase the mass flow rate anymore. So, then the mass flow rate remains the same. So, after C you may have different back pressures like D, then E, then F, and in between points whatever all the points that I have shown. With all these, the important point to note is that we can get different Mach number at the exit, but the mass flow rate becomes saturated once you come to the back pressure C. Beyond that you cannot alter the mass flow rate. Of course, you can alter the Mach number by using the physical phenomenon either inside the diverging part or outside the diverging part or at the exit of the nozzle. Okay. So, with this background which gives a design consideration for a nozzle based on what output you want. So, if your output is restricted within Mach number less than 1, you will traditionally go for the converging nozzle. If your output is restricted to Mach number greater than or is dealing with Mach number greater than 1, you should ideally go for a converging diverging nozzle, because in a converging section you will never get Mach number greater than 1. So, then what we will do is we will work out a problem to illustrate some of the concepts that we have learned from here. So, let me write down the problem in the board. So, this is a converging diverging nozzle, this is section 1, this is section 2, this is not the throat, right, any section 2, and this is section 3. So, A1 is 24 centimeter square, A2 is 18 centimeter square, A3 is 32 centimeter square. M1 is 2.5, P1 is 40 kilopascal, T1 is in this example you see that in the converging section itself the Mach number is greater than 1. So, you might ask that I have just now said that in the converging section it is not possible to have Mach number greater than 1. What I wanted to mean is that if there is already an inlet Mach number less than 1, we cannot accelerate that to a Mach number greater than 1 in the converging section. If it is already there at Mach number greater than 1, it will remain to be so and it may further reduce. So, you have M1, P1, T1, these data given. So, this section 2 is where normal shock occurs. So, this is normal shock plane. So, the first part is what is m dot 1, second is what is m3 and third is what is P03, that is the stagnation pressure at 3. See, the physics of the problem is that because shock is occurring here, the isentropic relationships will hold true from 1 to 2 upstream. So, we call this as 2 upstream and 2 downstream. So, from 1 to 2 upstream an isentropic relation will work, the flow will be practically isentropic. From 2D to 3 there will be isentropic relationship working until and unless there is a further shock in between, but between 2U and 2D the shock relationship has to be used, you cannot use the isentropic relationship. So, that is the whole understanding. Now, m dot 1, what is that? M dot 1 is equal to rho 1 A1 U1, okay. So, rho 1 is P1 by RT1 A1, U1 is M1 root over gamma RT1, right. So, you know T1, P1, A1, M1 everything you know. So, by substituting all these you will get 0.96 kg per second. So, once you do that, this is what is M1 dot, then next is what is M3. So, now to get M3 you must move along the flow where you first get what is the Mach number at the upstream of the shock. So, you know A1 by A1 star is a function of Mach number 1. So, this is A by A star as a function of Mach number for isentropic flow we have derived. So, from A1 by A1 star as a function of Mach number you can find out what is A1 star. A1 star is same as A2U star, right, because A star does not change till you have a shock. So, A2 by A2U star is a function of Mach number 2U, right. So, if you substitute all these, this is a quadratic expression A by A star as a function of Mach number. So, there are two possible Mach number solutions, one is greater than 1, another is less than 1. Which one will you take? You will take the one which Mach number greater than 1, because upstream of the shock the Mach number is greater than 1. So, you from here you will get M2U is equal to let me see if I have the answer. I do not have the answer, but this will be greater than 1, that much I can say. Numerical answer I do not have in my notes. Now, how do you relate M2U with M2D? For that you use the relationship between Mach number before and after the shock. So, M2D square is equal to M2U square plus 2 by gamma minus 1 by 2 gamma by gamma minus 1 M2U square minus 1. This is the relationship that we have derived, basically M2 square by M2 square as a function of M1 square for shock, normal shock. So, substituting M2U you will get what is M2D. So, M2D is 0.54977, this is the answer. So, once you get M2D, you know now A2 by A2 star is a function of M2D. A2 star is different from the A star in this section, because there is a shock that changes the A star, a shock changes the stagnation pressure, all these things happen because of the shock. So, when you have M2D here, so you will get what is A2 star, and A2 star is same as A3 star. See, M2D is 0.54977. So, now let us use this formula dA by A is equal to m square minus 1, the formula with which we started our class, 1 plus gamma minus 1 by 2 into dm by m. Okay. See, M2D is already less than 1. So, m square minus 1 is less than 1. dA by A in the section between 2 to 3 is greater than 0. So, and this is basically less than 0, not less than 1. M square is less than 1. So, that means dm by m has to be less than 0, negative. What it shows is that the Mach number further reduces from this in the diverging section, and there is no question of any shock or anything else. So, you can now calculate. So, A2 star equal to A3 star. So, now A3 by A3 star is a function of M3, right. So, given, so you know what is A3, you know what is A3 star, you will get two possible values of M3 from this quadratic relationship. So, which one will you take, greater than 1 or less than 1? You will definitely take the one with less than 1. So, M3 is 0.27. That completes the second part. For the third part, the method is very similar. Instead of using the instead of depending on the temperature, so or sorry, instead of depending on the A by A star relationship, we will depend on P0 by P relationship. P0 by P is also a function of Mach number. So, P0 by P, so you have a P here, then you have a P0 by P here, right. So, I am giving you the schematically. So, you have a P0 by P here, this is a function of the Mach number here. So, you get P0 here, the same P0 is here. So, you will get a P0 by P as a function of the Mach number at 2u, you already know what is the Mach number at 2u. So, you will get P2u, P0 by P as a function of Mach number you already know. So, given you already know M2u, P0 by P2u will be a function of M2u. So, you will get what is P2u. Now, you have a relationship between P2d by P2u, this is P2 by P1 across the shock as a function of M2 by M1 across the shock. So, from here you will get P2d and P0 by P2d is a function of M2d. This P0 is new P0, that is P0 at 2, which is downstream P0 2d. Okay. So, from here you will get what is P0 2d, this is same as P3 P03, right, because the stagnation pressure will not change without the existence of any shock, right. So, let me summarize the strategy, very simple. You have P0 by P as a function of Mach number, that is what you are using. So, from that you get P0 here, the same P0 is here. So, P0 by P2u is a function of M2u, from there you will get P2u, P2d by P2u is a function of M2d by M2u or M2d and M2u. So, you put M2d and M2u, you will get a P2d. P02d by P2d is a function of M2d, from there you will get P02d, which is same as P03. So, if you work out all these, 435 kilopascal. So, we stop here in this lecture, we will work out more problems in the next lecture. Thank you.